So, we are back with one more live stream tonight. Thank you for joining if you're going to be joining. And also, thank you for finding this video upload later on. If you're going to be finding this video upload later on, welcome, welcome. We will get started. I have in front of me Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. It's a book that we have been referencing a lot lately for our topics related to dark matter and some dark matter candidates and things like that. So we have been covering these topics, and also we've discussed some of my own research as well, which is in neutrino physics, and how there are certain similarities between. Oh, hi Clicker, hello. Clicker says hi. Neeraj says hello, namaste. How are you? Hello. So yeah, we talked about dark matter recently. I think for a couple of lives now, we've been covering this topic, and also let me read a message. Okay, perfect. So we've been covering this topic. We've been hanging out with the kitty cats, and I thought that because we talked a lot about 20th century physics, especially in the first half century of the 1900s, pretty much all the different developments that happened at that time, we spent a lot of time doing that. So that kind of brought us to certain open questions of today, of the current times. And that's kind of where we are now, which is that the two top questions as of right now in the world of physics are, of course, what is dark energy? It started with the cosmological constant, and it's a very big, if not the biggest question in physics and or in cosmology today. And then the next biggest question, or the next biggest, most open question right now in physics and this universe, is what is dark matter? So that's sort of where we are now. We're trying to address these things and trying to learn the work that has been done already. So that's what we'll cover again today. Settle in for this chat. We won't be in a rush. You know, I still have to make some tea, actually. I got this started so that people can have a chance to kind of join and settle in. I'll show you the books that we're going to be covering and everything like that today, and let you get settled and make some tea. Hello, everybody. Thank you for joining. Thank you. I was just mentioning that we're getting started with the live for today. We will cover some astronomy and some discussion about dark matter, and also kind of bring everybody up to speed on how astrophysics is done in today's times. So that's the topic, and I will also let you look at the books that we're going to be covering so that you know what what the topic is today. Change to coffee break. Yes. So indeed, we will be taking a break, actually. As in, I do need to make a tea right now, actually. 1 second, sorry. Where is a good spot? Let's see. Hi, Niraj. Burn thy priest. Astronomy is astrologic, right? You mean astrology? No, it's not astrology. It's astronomy. Hi, Maria. Maria Isabel Marquez says hi from Mexico. Hi. Hello. Hi. Yes. Hi, Maria. Thank you for joining. Welcome. Hi, Clicker. Hi, Neeraj. Hi, Burn Thy Priest. Hi, Maria. Welcome to Mexico. Thank you for being here. Welcome. Hello. Hi. Okay. So I still need to do a few things. I need to set up the kitty cat's water, and I also need to make my own boiling water and tea and such things. So yeah. So yeah, welcome to the live. We're just gonna be making some tea and then getting started with the topics for today, and also reading from this book, Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. What are you doing? Burn Thy Priest says, what's the difference? Maria says, what are you doing? Me resting from my children. Good job, Maria. Welcome to this live. Yes, please rest. Please make some tea if you can and just relax and be with us. Neeraj says, Kya aapne khana banaya? No, I did not make any food. Well, actually, no, I did. Hi, Death Dragon. Death Dragon, how are you? Death Dragon is a mod for the channel. I've been waiting all day. Oh, I'm so sorry. Well, it's late for you, Death Dragon. You might have to... Oh, that's right. Tomorrow is off. Are you up late because tomorrow is Thanksgiving? Happy Thanksgiving, everybody. And I did make some food earlier today. It wasn't a lot of cooking, but I made some dumplings. So yeah, thank you for asking. Thank you for being here, everybody. I've been waiting all day. Aw, sorry about that, Death Dragon. Are you, yes, I have no bedtime. Wow. So, Death Dragon, do you have Friday off too? Dumpling से पेट भर जाता है आपका? हाँ जी. I do have, I ate quite a few dumplings. I don't have to go to bed. Death Dragon, really? Are you sure? Are you sure? Because aren't you too young to not have a bedtime, Death Dragon? Are you sure, my child? Slash my friend. Okay, sorry about the delay. All right. Let me read your comments. Please don't spam. Hi, now Seth. Death Dragon, I know now Seth. I have Friday off and today and Saturday. Okay, good. Now Seth is good. Now Seth. I have a new iPhone 15 and I'm using it right now. Wow. Yeah. Thank you, Death Dragon, for being such a good mod. And yeah, welcome to Now Seth and everybody. Thank you for being here. Death Dragon is gonna mod. So Death Dragon, just watch out for anybody who's being creepy. I appreciate your help with moderating that. Otherwise, I think most of the late live people are actually friends and they're all good. So don't worry about it. I have Friday off and today off and Saturday off. Wow, Death Dragon. So you have a number of days in a row off. Are you excited? What are you going to be doing tomorrow? What's the plans for tomorrow? No, baby, Fuji Garna, Shana. Garna, Fuji. Oh, I'm so sorry, Fuji. All right, so I'm cleaning the teapot. Hi, now, Seth. Hi. I see your comment now, Seth. Maybe don't say the same thing too many times, otherwise I can't read the other people's comments. Yes, please don't. Yeah. See, I want to be able to read other people's comments too. But yeah, thank you everybody for being here and for joining. Oh gosh. Death Dragon. Oh, you can time him out for a little less than that. Is that 5 minutes or what? Him or her, I actually don't know. Sorry. Death Dragon is a very strict mod, I'll warn you guys. He's very strict, so just be a little mindful. Oh my gosh, Death Dragon, you have taken out the dragon slaying hammer here. So, sorry, yeah. Give me 1 second. I actually gonna eat something as well. Fuji. And I'm gonna make my tea. Give me 1 second. Everybody, thank you for being here. Oh man, what's this? I had to hide a pot from Fuji earlier. Oh my god. Fuji, this is not good. Fuji. Oh my gosh. Fuji is being so naughty today. So naughty. Fuji. No Fuji. Okay. Ooh, let me show you. My water's about to boil. Ooh, let me show you. This water's about to boil. Pretty blue color. I got a new iPhone 15 and I'm using it right now. Dead Dragon, please open the book. Yes, will do. Hi Betsy. Sorry about the delay. We will open the book and start reading in just a second here. Here's the bubbles that are coming. Aww. So, in just a second here, we will start talking about astronomy. I'm thinking we will read something introductory from the book and go from there. So, you said to open the book, so why not? We can open it. Where's Baji? Baji's right there. So, here, you can look at the contents here. For a moment. Fuji! Fuji no! Fuji no! Fuji's trying to eat some of the leftovers. Oh gosh. I dropped something. Oh, I made a mess. Usually I'm not the one that makes the mess around here, but I did. Oh god. Oh no, no. Okay, let's see, where is Baji? I showed you Baji. 1 second, 1 more second, babies. Or not babies, you guys. I'm looking at my babies, so I thought about that. 1 second. So I know some people like to see the bubbles, so let me show you. Yay, bubbles! Yay! Bubble, bubble. Bubble, bubble. I love this part. Phase transition. Fuji, Karnashona. Fuji, please get out of the sink. He is, Fuji's getting into massive amounts of trouble here. Fuji, I'm not appreciating this at all. In fact, this is not good for you, Fuji. Not good for you. Don't try to beat me. Don't try to. Is that good for you? No, it's not. So, are you going to continue to do that? No, you're not. Let's go. Let's go. You're so wet, Fuji. This kitty cat doesn't even care about being wet. He likes oil and dairy so much. Baji, can you Fuji, you've been very, very bad. This one's Baji. Hi, Baji Babu. Hi. Hi, Baji. Hello. Baji. Fuji. Yes. Here's Baji. Here's Fuji. Fuji has lots of designs here to be extremely bad. Fuji, Mama is watching you. Don't try. As I make the tea, he knows that I'm dealing with something hot and have to be careful. So I get distracted, and as soon as I do something, he plants up. Oh, look at him running towards the sink. Fuji Babu. Fuji. Mama is very disturbed by this. Fuji. Fuji. And he does not like when I take him out of the sink. What is wrong with you, Fuji? And we're out of paper towels, so I can't even clean the mess that I made trying to do all this. It's okay. All right, guys, give me 1 more second, please. There is just a mess of things going on here. Okay, let me clean the sink. Alright, here we are getting the tea out. tomorrow I have some Thanksgiving plans myself. I will be going to my friend's house, and I will be over there. Oh gosh. Oh gosh, oh gosh, oh gosh. Okay. Alright. Up and vertical. Up and vertical. Off. 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 Off and off and off. Okay. Off and up and vertical. Off. Up and vertical. Off. Vertical. Off. Just have to make sure everything good. Yeah. Okay. All right. So everybody, thank you for being here. Okay, so I was thinking, let's see. I know we have talked about dark matter and candidates for dark matter in the past. As in, for the last couple of lives now, we've been talking about that. So now I'm thinking, and sort of some of the things that came up were sort of, I felt like it would be good for people to get more of an introduction to astronomy and how astronomy is done historically. Because I mentioned about sort of the, how astronomy used to be done historically, traditionally with visible light, and how it's come a very long way now where we can do astronomy with more types of light, you know, not just visible light and optical light, the stuff that we can see, but also gamma rays, x-rays, all kinds of things like that, all types of light, radio waves, as well as we now do astronomy with particles. So to kind of appreciate that, I thought it would be good to get into a little bit of an introduction here. So we will get into that in just a second here. I do want to eat something actually. But yeah, I think that's what we'll talk about today. What does people think of that? And also I can read your comments if you have sent me things. If you have typed things, I will read them here in just a second. Actually, where's my iPad? I'm gonna share the live as well. Excuse me. There's nothing for you here, Fuji. It's not for you. Definitely not. Fuji. No. Okay. I see the live on my phone, or not phone, iPad. I'll let everybody know that we're live. Hi, Fuji. What's wrong? Oh my god. Baji and Fuji are being really bad. Oh my god. Okay. So, Baji thinks he's about to be fed. But this food is all mine. Mm-mm. Mm-mm. We also have this book, by the way, that we will get into. We have all kinds of plans today. Mm-mm. What is it, Baji? What is it? Look at that. Mm-mm. You've been given your snack. I'm not sharing my snack with you. Mm-mm. Indeed, no. No, indeed. Baji wants my food. All right. I'm gonna wash my hands. Get started. It's time for Baji. It's time for astronomy. Hi, Sofyan. Hi. Sofyan says hi. Hello. It's time for astronomy. Mama has eaten food from bakery. Thank you for the food. Okay. So. Okay. Baji, I'm going to hide my bowl from you. And we will study astronomy. These two are getting into so much trouble. Okay. All right, everybody. Thank you so much for being here. We will talk about emergence of modern astronomy. So we kind of mentioned how traditional astronomy is just looking up at the night sky. Thank you. Sofian says, beautiful cat. Thank you so much. Bellissima. Baji. So we know that astronomy, we kind of talked about how, well, centuries ago, we looked up at the night sky and, we looked at all the bright objects in the night sky, the stars, and we can just see that with our naked eyes. In other words, we were doing astronomy by just looking up at the night sky with our eyes and just using visible light or optical light to do astronomy. And, people were very good at the night sky back in the day. They studied it with a lot of time and were able to kind of note what things were where, constellations, things were given names. A lot of astrology also is done with that, even now. And like things moving, in and out of position, something like Mercury being retrograde. That's all basically doing sort of a observation of these different objects in the sky and understanding how their motion or how their positions change, basically. So in that sense, we've been kind of doing astronomy and observing the night sky for a very long time. So I think this chapter will give us a little bit more information as to that. So we'll read it for at least a little bit over here. So modern astronomy has deep historical roots. The main path of development for astronomy begins with the ancient Babylonians. Greek astronomers built on the observations of the Babylonians, creating a science of astronomy that was mathematical and deductive in nature. So yeah, people got really good at knowing what things were where in the sky and drawing out the different shapes, and it was easier to group things, and so they even, came up with constellations and understood the shapes of those and what groups of things went into which constellation. Now, of course, we know that when we look up at the night sky, most of the things we see are actually galaxies. But even a bit over 100 years ago, or maybe even 100 years ago, we actually did not know that there were more galaxies. Even beyond our own Milky Way galaxy, our own galaxy, home galaxy, there are actually many, many, many galaxies. And until Hubble gave us an observation and gave us the data on this, we actually did not know about that. So that was a big revelation in the 1900s. In the 20th century, in other words, part of the richness of the 20th century and everything that it had to offer, including relativity, astronomy, special and general relativity, that is, as well as a lot of developments in quantum mechanics. But what might have come as a shock later actually gave us a lot of information, revealed a lot about this universe and our neighbors. There's other galaxies, and we can study them. Turns out that the universe is expanding, not only expanding, its expansion is accelerating. And also turns out that we didn't really, even though we understood and found out so much about even the other galaxies, the fact that they exist, and some of the shapes and things like that as well, and what the nature of these other galaxies were like in terms of sort of their structure, formation, and all that. But turns out there are questions that remain both near and far. There are things even about our own galaxy that we are still answering. And one of the biggest questions that I was also mentioning earlier, of course, is about dark matter. The fact that we sort of have this more mass than we can account for in the halo of our own galaxy gave rise to this concept of needing dark matter, matter that is dark or invisible, does not interact with light, and we don't know exactly what it is. But here we will talk about early astronomy. So Greek astronomers built on the observations of the Babylonians, creating a science of astronomy that was mathematical and deductive in nature. ancient knowledge about the heavens was preserved and expanded during medieval times by Arabic scientists. During the Renaissance, the heliocentric theory of Copernicus led to additional advances by scientists such as Galileo and Kepler. This lineage, Babylonians to Greeks to Arabs to Europeans, is a great oversimplification of the rich history of astronomy. However, in a single chapter, we have only enough space for a broad overview of how modern astronomy evolved. So, astronomy is one of the oldest sciences. As you probably are aware, astrology is also very old. But so is astronomy, the study of the heavenly bodies, understanding our own solar system and beyond. Pretty much the night sky is astronomy, studying it and trying to collect data nowadays with more modern technology, of course. But it is something that has really evolved up until now, from, as they mention here in this book, Babylonians to Greeks to Arabs to Europeans. So we have been, let's say, a fan of the night sky and also kind of trying to study it for a very, very long time. It's really nothing new, but it has evolved. So, early Greek astronomy. So, there is a lot that has been contributed to the field by all kinds of different people across the world in different periods of time. We just mentioned, of course, the heliocentric theory of Copernicus. That itself was a very big deal because people used to think that the Earth was in the center, geocentric theory. But to turn that over and say, and actually, not only did we think that, we actually made the math very complicated, trying to make the geocentric theory work, because we thought that we're very special being on Earth, and here we thought we were the center of the universe. We actually did not really know, first of all, the extent of the universe. We didn't even know until much more recently that, for example, that we're just, a tiny part in our own galaxy, and there are, in fact, many, many other galaxies. We're not that important or special after all in that sense, but maybe special in other ways. We can even talk about that too, how we are special. But on the grand scheme of things, for the most part, we realize we're not that special. And the heliocentric theory in itself, saying that the sun was at the center of our solar system, and then, of course, later on, Galileo worked on it, and Kepler gave us, not circular orbits around the sun, but elliptical orbits, and the Keplerian laws and things like that. And then Newton came along. All of that work in itself was... I had to put text tones and ringtones on my contacts. Sorry, but I'm back. Read this comment, please. Okay. Thank you, Death Dragon. We will be talking about mainly astronomy, so we might not read all of your comments. Just a heads up. Thank you. So, we will be reading your comments, especially if they're related to the topic we're discussing or something science related, but I don't know if that I will read every comment. That's not relevant. But thank you for being here and welcome to the live. So, I just wanted to mention that part before we keep going, which is that just making the sun sort of the center of the solar system in itself was a big deal. Now we will look at early Greek astronomy. Of the 9 muses of classical mythology, 8 dealt with various forms of music, dance, and poetry. The 9th muse, Urania, was the muse of astronomy. This is indicative of the ancient Greek approach to astronomy. The motions of sun, moon, and planets were regarded as a type of cosmic dance. Yes, I did. Revealing an underlying rhythm and harmony. A main goal of ancient Greek astronomers was to build, using deductive reasoning and mathematical computations, a conceptual model for the universe that explained the sometimes complicated motions of celestial bodies. To provide a bit of clarification, when historians of science talk about ancient Greek astronomy, they aren't talking solely about developments in the geographical region currently called Greece. Rather, they embrace the entire Greek-speaking world, which in Hellenistic times, after the conquests of Alexander the Great, embraced much of the Mediterranean basin and the Near East. So that's kind of cool. When we talk about Greek astronomy, we don't just mean the current geography of Greece, but more broader region, much of the Mediterranean basin and the Near East, and pretty much everybody who spoke Greece, so, or spoke Greek. Our knowledge of Greek astronomy, particularly in the time prior to Aristotle, is sadly fragmentary due to the incompleteness of the written word. So in the old days, it was hard too because we didn't really, until we started printing and publishing, things were difficult to pass on information, and record keeping was not really as much of a thing. So it really greatly helped when we started to publish and things like that. But many early Greek astronomical works are lost and are known to have existed only because they were cited by later writers. Some general aspects of Greek astronomy are well established, however. For instance, the Greeks were the first known culture to realize that the sky is three-dimensional. That is, it has a significant depth. Earlier societies, such as the Babylonians and Egyptians, thought that the sky was a thin, solid dome arching over a flat earth. Wow. So the sky, they thought that it was a thin, solid dome arching over flat earth. The most famous written description of such a domed universe is in the great book of Genesis. How interesting. God made the firmament and divided the waters. So this is a quotation from this book. Okay, we're reading this book. So when there's a quotation, I'll let you know so that it's not, God made the firmament and divided the waters which were under the firmament from the waters which were above the firmament, and it was so. And God called the firmament heaven. Greek astronomers, however, realized that the sun and the moon, instead of being disks stuck to a domed sky, were spherical objects at different distances from the earth. So that's a big one, because if they were thinking that this was just a dome, they could have been just disks, but now people knew, probably by studying all the phases of the moon, especially as well, that these were spheres. I'm just guessing, though. We will find out. The realization that space was three-dimensional led Greek astronomers to an understanding of various celestial effects. For instance, they correctly explained the causes of the phases of the moon. Oh, good. Okay. I think the phases of the moon, the fact that the moon changes, that there is like a crescent moon, bigger moon, slightly, gibbous, full moon, new moon, all those phases of the moon. That's what I mean. Like the size of the moon as we see it is changing day to day because of the phases of the moon and its motion around the earth. So during the course of 29.5 days, the moon appears to change in shape against the sky. So if it was just a stuck disk on the dome, then that would be kind of hard for it to change phases, right? So they guessed that it was actually a sphere. During the course of 29.5 days, the moon appears to change in shape against the sky. The moon wanes from a full circle on the sky, the full moon, through gibbous and crescent phases until it seems to disappear. So those are the phases, broadly speaking. The full moon, full circle on the sky. Gibbous is sort of not really a full moon, kind of smaller than a full moon. Crescent, of course, is the nice, pretty shape of the crescent moon. And until it seems to disappear, as in it goes dark, which is the new moon. It then waxes through the crescent. So as it gets bigger, we call it waxing. And as it gets smaller, we call it waning. So waxing moon versus waning moon. It then waxes through the crescent and gibbous phases until it reaches full moon again, 29.5 days after the previous full moon. The ancient Greeks realized that the phases occur because the moon is an opaque sphere illuminated by the sun. So that's a big deal. They realized it's an opaque sphere illuminated by the sun. Actually, the moon, our moon, by the way, just so you know, is one of the largest moons in the solar system. We have what they call a giant moon, actually. So I will say we only have one moon. Most other planets. I think all other planets have more than one moon, if I'm not mistaken. We just have the one, but it is one of the bigger ones. So at least we have that. So because the moon is pretty big, you can actually even make out the sort of the features of the moon on, the sort of the craters and mountains and things on the moon. So I think they were, and with less pollution and light pollution and things like that, I think people were able to see the night sky much better than we kind of do now. And so that probably helped. So the moon wanes from a full circle in the sky, the full moon through gibbous and crescent phases until it seems to disappear. It then waxes through the crescent and gibbous phases until it reaches full moon again. 29.5 days after the previous full moon. The ancient Greeks realized that the phases occur because the moon is an opaque sphere illuminated by the sun. As the moon orbits the earth, we see different fractions of the illuminated hemisphere of the moon, causing the apparent change in shape. The Greeks also realized the causes of eclipses. So that's another thing. You would think something like a lunar eclipse or a solar eclipse would be really upsetting if you didn't realize what was happening. But as they happened, they figured it out. So the Greeks were really smart. During a lunar eclipse, the moon darkens dramatically. This is because the moon passes through the Earth's shadow, depriving it of the sunlight that usually illuminates the moon's surface. So the moon is lit up by the sun. So if the Earth is in the way, it will get dark. During a solar eclipse, the sun darkens dramatically. This is because the opaque moon passes between the Earth and the sun, blocking the sunlight that usually reaches the Earth's surface. Thus, Greek astronomers realized that the sun is farther away from us than the moon is. So how cool is that? So it's because, the moon is in the way, is why the sun even gets blocked sometimes. And that told them that the sun is farther away than the moon because they didn't really know all these different distances. So that's really cool. That's really smart. Aristotle, who lived from 384 to 322 BC, so 384 years before BC to 322 years before the birth of Christ, sorry, before BC, before C, I guess, was one of the great philosophers and scientists of the Greek world. In his work On the Heavens, you know what I should do? I should find Aristotle's works in the library. Maybe I can find it. In his work On the Heavens, written around 350 BC, he turned his attention to astronomy. In this work, Aristotle pointed out that the Earth was spherical and gave 4 physical reasons based on observation why this must be true. His first reason was based on his observations of how gravity works. Since gravity draws dense materials toward the center of the Earth, the resulting compression must squeeze the Earth's substance into as compact a form as possible, which is a sphere. His second reason was based on observations of partial lunar eclipses. When the edge of the Earth's shadow falls on the moon, it always forms an arc of a circle. So he kind of looked at how the Earth's shadow was looking on the moon. So it's almost like we're on the Earth. It's spherical, but since we're on it, we might not be able to see that. But you can see our shadow on the moon. So he's like, okay, look at that shadow. It's always forming an arc of a circle, the only object that always casts a circular. And so he, looked at after several lunar eclipses and never seeing it form a different shape. The only object that always casts a circular shadow is a sphere, thus the Earth must be spherical. His third reason was based on observing that new stars appear above the horizon when you head south toward the equator. Oh my gosh, that's right. Look at that. Of course. So see, you'd have to be very familiar with the night sky. And of course, it helps if you can see a very clear night sky and you would kind of know what stars you usually see, what things you usually see, where things are, what shapes and everything. And if you see new stars appearing, then you know that you've uncovered by going down. So his third reason was based on observing that new stars appear above the horizon when you head south toward the equator on a spherical Earth. Observers at a latitude L north of the equator cannot see stars with declination less than minus 90 degree plus L. So, to take an example known in ancient times, the star Canopus, which is at a delta of minus 53 degrees, sorry, a declination of minus 53 degrees, is invisible from Athens. And Athens' latitude is around 38 degrees north, but is visible from Alexandria, which is in Egypt, which is around latitude of 31 degrees north. So, he figured out that there is a star that is invisible from Athens, but if you go to Alexandria, then you can see it. This showed that the Earth was curved in the north-south direction. It's not, not only is it not flat because of the other reasons, but it's curved in the north-south direction as a sphere would be. His fourth reason was based on observing elephants. Wow. Oh, this is so interesting. This is so like amazing because, back in this time, of course, we didn't have the technology we have today. We didn't have airplanes, we didn't have satellites, we didn't have spacecraft. So it's just making these simple observations that he's able to conclude all this. So Earth is curved, so when you go down, seeing a new star appear, well, that's amazing. And that shows the dedication to understanding and learning the night sky. This showed that the Earth was curved in the north-south direction as a sphere would be. His fourth reason was based on observing elephants. Since elephants existed both in Morocco, the westernmost region known to Aristotle. So Morocco was the westernmost region, wow, known to Aristotle, and in India, the easternmost region known to him. The two regions must actually be adjacent to each other on the spherical surface of the Earth. This last elephant-based reason sounds absurd to modern ears, but it's actually an illustration of how you can arrive at the right answer for the wrong reasons. So he's thinking that elephants existed both in Morocco as well as India, and they are west and east, and maybe they went all the way around. The astronomer Aristarchus. So not Aristotle now. We are now moved on to the next one. 310 to 230 before Christ, okay, BC. So now we are more, more modern. It's a backward kind of number, so yeah, 310 to 230 BC. Astronomer Aristarchus was notorious in his day for his unprecedented belief that the Earth orbits the sun rather than vice versa. Oh my gosh, that's right. So I think I took this in the history of science class. I'm back. I played a little bit of Roblox. That's okay. All right. So I think I remember this from my history of science class at NC State. That was, by the way, one of the most amazing classes I've ever taken. Like, if you're going to take a history class, sort of like as one of those general ed classes, I thought the history of science class at NC State was amazing. And this was all covered there, but it's still fun to read it here. The astronomer Aristarchus was notorious in his day for his unprecedented belief, as in nobody else believed him or believed this, that the Earth orbits the sun instead of the other way around. The only surviving book of Aristarchus on the sizes and distances of the sun and moon doesn't explicitly mention his heliocentric or sun-centered model for the universe. Instead, it puts forward geometric methods for determining the relative distances to the sun and moon and their relative sizes. Fuji, what's up? কি হয়েছে সোনা? Hi, my first time watching your stream. Hi, Steven. Thank you, Dead Dragon. I think on this live, most people are going to be pretty fine. Don't worry about it too much. I respect all streams. Thank you, Steven. We just have a very excited mod. Um, Fuji, my baby Fuji has just gone upstairs. I don't know why. Baji's here though. Thank you, Steven. Thank you, Death Dragon. Thank you, everybody, for being here. But yeah, Aristarchus, who was born 310 BC. Love your kitties. I have 3. Thank you. Me too. Reese, thank you. Thank you for joining. Hello, Reese. Yeah, we have Death Dragon in the chat. He's a young friend of this channel. And this is past his bedtime, but he is convincing me that he can stay up because of Thanksgiving tomorrow and Friday being a holiday and Saturday being Saturday. So, yep. So just beware, everybody. Death Dragon will cut you. Just, I'm almost scared myself. I don't want to lose my viewers. We kind of need the watch time here. So it's like Mr. Kitty, Osha, Luna. Oh, wow, those are really pretty names. Mr. Kitty, Osha, and Luna. Aw. This one's Baji. Anyway, so we'll talk about Aristarchus. Aristarchus realized that when we on the Earth see half the moon's disk illuminated, then the Earth-Moon-Sun angle must be exactly 90 degrees as seen in this figure. See? Right there. Where this is the Sun, Moon, and Earth. So when the Earth-Moon-Sun angle is 90 degrees, then the ratio of the Earth-Moon distance A to the Earth-Sun distance C is A over C, given by cosine theta, some trigonometry, where theta is the measurable angle between Sun and Moon as seen from the Earth. So unfortunately, so look at this. Trigonometry. This type of math is quite old. Comes from these days of Aristarchus, if not older. I forget exactly, but here it is. We're doing trig, where theta is the measurable angle between the Sun and the Moon as seen from the Earth. Unfortunately, the angle theta is difficult to measure with sufficient accuracy since the difference between theta and 90 is very tiny. Aristarchus thought the angle was theta equals 87 degrees, which would give this equation. And eventually we get this because of the difficulty of measuring theta with sufficient high accuracy. Aristarchus underestimated the distance to the Sun. So look at this. He did some trig to figure out the distance to the Sun because of the trigonometry of that triangle right there and getting these cosine thetas and everything. But because the difficulty of measuring theta with sufficient high accuracy, Aristarchus underestimated the distance to the Sun relative to that of the Moon by a factor of 20. But at least he tried, and this is awesome that he tried and got to something. Nevertheless, Aristarchus did correctly deduce that the Sun is much farther away than the Moon is. So this is probably one of the first instances of trying to figure out what is the distance of the Sun from the Earth. And by the way, that distance of the Sun from the Earth is a very important distance. It is often used as a common unit in astronomy. So, after some more efforts or some more attempts, we did, more correctly measure this distance. But you can imagine all those years ago, hundreds of years before the birth of Christ, as in a very old time ago, people were trying to measure this distance, and they even did trigonometry to do that. And that's really, really, really cool. I love astronomy. I used to have a telescope as a kid. I could. Yes, I love astronomy too. I used to have a telescope as a kid. I could ID all of I could identify all of Jupiter's four big moons. Oh, nice. I've seen Jupiter's moons too. That's really cool. Yeah, amazing. I love the looking at Jupiter. It's so nice. And seeing its moons, and you have to wait for a long time sometimes to get it all. I think one time I actually used to organize night sky watching parties when I was in college. And like I basically would announce that we're going to do it. And then I would make all my friends and fellow physics majors go with me and drive all of us out to like the woods and very dark place that I would definitely not know how to get to. I was an international student in the US. And so I would make everybody, like, I would set the date and the time, and I'd be like, okay, everybody. Ooh, and we borrowed telescopes from the physics department, which is like a combined physics and astronomy department. And actually, at these sky watching parties, we had a lot of fun. We did camping and like marshmallows, though that was my first introduction to like the fun things that people do in America, like making fires and making marshmallows and things like that. So yeah. And yeah, so some of those people I'm still friends with. They're all over the country. And yeah, so all I remember is getting the telescope set up is like the biggest part. It takes forever. And then to like make sure everything is, pointed correctly, and resolutioning is resolutioning. But yeah, I did see the four moons myself as well. And it's really, really, really cool. I meant ID. Yeah, I got you. Death Dragon says thumbs up. Sometimes I could see the red spot. Sometimes I could see the red spot. I did it in my backyard. Oh, wow. So your backyard must be dark enough to be able to see Jupiter and its moons. Wow. The red spot on oh wow. The red spot on wow. Oh, that's really good. Yeah, I think being able to see Jupiter on a telescope is really, really awesome. That's great. Death Dragon, I love you guys. Yay! Thank you. Yes, we're all friends here, Death Dragon. I think we're gonna be okay. But yeah, if you see anybody creeping, feel free to give them a warning and then maybe time them out. Don't time them out right away. When I'm more famous, you can cut their heads off more quickly. So, because of the difficulty of measuring theta, Aristarchus actually underestimated the. So, Aristarchus thought that the sun was a bit closer than it actually is. But he still did know that it was farther away, obviously, than the moon, and, very, very far, much, much farther away than the moon is. Since the sun and the moon are the same angular size. So, isn't this so cool, though? The sun and the moon, obviously they're at different distances from the Earth, but they have the same angular size as seen from the Earth. That's so cool, though. It blows my mind, honestly. It has the same angular size as seen from the Earth. We know from similar triangles that the ratio of their diameters is the same as the ratio of their distances from Earth. That is, Aristarchus thought that the sun was 19 times bigger than the moon in diameter, whereas the sun is actually 390 times bigger than the moon. Aristarchus knew that the moon was smaller than the Earth, since it fits inside the Earth's shadow during a total lunar eclipse. Moreover, he calculated by further geometric arguments that the diameters of Moon, Earth, and Sun had the approximate relative values of 1:3:19. Again, although the exact numbers are wrong, they're actually closer to 1:4:390. Aristarchus correctly deduced that the Sun is much larger than the Earth, thus lending support to, or perhaps even inspiring, his heliocentric model for the universe. So he was on the right track by a lot. He made really good progress. It seemed sensible to Aristarchus that the small Earth should go around the large Sun rather than the reverse of that. That's so cool. It was fun seeing comets passing by. My dad once said you'd be lucky to see one comet in your life. I've been lucky to have 4. Wow. I think I've seen comets, but I feel like there was one night when it was like good for that. But I'm not so lucky at seeing them actually. Yeah, that's really good. So anyway, Aristarchus deduced the relative sizes of the Moon, Earth, and Sun, absolute values for their sizes. Oh, Fuji's back because of their snack falling. Absolute values for their sizes in physical units were provided by the work of Eratosthenes, who served as the head librarian of the famous Library of Alexandria. Ooh, famous Library of Alexandria. Now I want to go to Alexandria. That sounds like a good plan. Although the original works of Eratosthenes have been lost, a later textbook by the astronomer Cleomenes records the method by which Eratosthenes determined the circumference of the Earth. Eratosthenes was aware that exactly at noon at the time of the summer solstice, the sun... Ooh, so quiz question for you guys. When is the summer solstice? Death Dragon can go first. The sun was at the zenith, as seen from the town of Syene, the modern city of Aswan in Upper Egypt. On the same date, however, the sun doesn't pass through the zenith as seen from Alexandria. Instead, look at that. That is so clever. We know he kind of knew that this same day, the sun does not pass through the zenith as seen from Alexandria. So there is an angle alpha south of the zenith at noon. At this point, Eratosthenes measured the angle alpha and found it to be 1/50th of a full circle. Wow. At this point, Eratosthenes assumed that the Earth is spherical, which he already knew from Aristotle, and that the sun is far enough away from Alexandria to the sun line, is far enough away that the Alexandria sun line is effectively parallel to the Syene sun line. So he's like, wow, look at that. Alexandria to the sun versus Syene to the sun are basically parallel. That's how far the sun is. And my first was Halley's, the one that struck Jupiter half bop, and the one that passed by this year. The longer day in summer, if I remember. Yes, summer solstice. Do you know the date for summer solstice? We have summer solstice. Winter solstice is coming up. December 22, 23-ish. Summer solstice is... Someone will say it in the chat. So, wow. So with all this, he kind of did some more math. Look at that. So it's so sweet that they were looking at Alexandria to the sun versus Syene to the sun. So much astronomy was happening in these in that particular area. Not too far from each other, but they noted how things were different between Alexandria versus Syene. The distance between Alexandria and Syene was known to be 5,000 stades. The stade was a Greek unit of length based on the length of the stadium in which foot races were held. This meant that the Earth's circumference was 50 times 5,000 stades, or 250,000 stades. Wow. So stades, this unit, interesting unit, was used to figure out the Earth's size as well. The length of the stade was not uniform throughout the ancient world, and historians of science have had a grand time debating the exact length of the stade used by Eratosthenes. Perhaps the most widely used stade at the time of Eratosthenes was the Attic or Athenian stade, equal in length to 185 meters. So from that, we got 46,000 kilometers. This is only 15% bigger than the correct value of 40,000 kilometers. So, thus, by the time of Eratosthenes, Greek astronomers not only knew that the Earth is spherical, but also had a reasonably correct idea of its size. Wow. I forget, to be honest. I think it's June 21st, right? Summer solstice. I don't get it. Okay. That's okay. You can also Google it. Summer solstice, I think, is, I think it's June. Because June 21st is probably summer solstice. Then we have the autumnal equinox. Then we have December, the winter solstice. And we have spring equinox. Those are the four important. So this is super duper progress. They knew the size of the Earth pretty much at that point, really early on. So a couple hundred years before Christ, the Greeks knew that the Earth is spherical and pretty much what the size of it was. That's really cool. Hipparchus, who is from 190 to 120 BC, was perhaps the greatest astronomical observer during antiquity. Hipparchus is credited with a number of accomplishments. So these are now bulleted. He has so many. All right, ready? Hipparchus produced an accurate catalog of hundreds of star positions. Wow. So now it's not just casually looking at the night sky. He actually cataloged a number of star positions. That's really awesome. I'm impressed. Give me 1 second. I need to take some sips of my tea here. Ooh, 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 ooh. They got really serious, the Greeks, about astronomy. Oh, yeah, it's a crazy day. I live in Virginia and had the full solar eclipse this summer. That was so cool. The daylight dimmed so much. I was in my yard working when the eclipse happened. Where was I? I think I traveled maybe that day. Yeah, it was a crazy day. I I had a flat tire that day, actually. That's what I remember. It was crazy. I had a flat tire. It was very scary. Ooh, some car almost ran me over that day. And I was also driving at a very bad time. It was awful. I should not have been driving at that time. I was trying to get to work because I think I had some kind of travel. And then I came back and I really should have taken the day off, but I decided to still go in for whatever reason. And it's like the middle of the afternoon, and some car at a roundabout basically tries to like run me over or something, like gets very close to me. So then I swerve a little bit to the right, which is the curb. I hit the curb and I get a flat. So, yeah, your story is better, Stephen, for your solar eclipse. Instead of seeing the solar eclipse, I think I was dealing with all this. But yeah, I got a flat. I think it was Yeah, it was pretty bad. But I did learn a lot about my car in the process of this whole thing happening. Yeah. It's 1 in the morning. Yes, Death Dragon. It's very late for you. You should really sleep now. Young people should be in bed by now. Okay. I need to. Hi, Baji. 1 second. I need to put the. It's Thanksgiving. Happy Thanksgiving. Yes. Happy Thanksgiving, everybody. I need to add some more water into my drink here. Sorry. Give me a momento. Baji, come. Come, Baji. You can sit. You can sit with Mama. Okay, let's real quick read about Hipparchus. Hipparchus's accomplishments. So he produced an accurate catalog of hundreds of star positions. It was his careful observations that led Hipparchus to the discovery of the precession of the equinoxes mentioned on page 14. So we will talk about we didn't really talk about that, but I actually just mentioned about that. He noted that the bright star Spica, which lies close to the ecliptic, was 6 degrees west of the autumnal equinox. I was mentioning about the equinoxes. However, a star catalog made 150 years earlier had described Spica as being 8 degrees west of the autumnal equinox. Hence, Hipparchus deduced that the equinoxes were slipping westward relative to Spica and the other stars at a rate of 2 degrees per 150 years, equivalent to 48 minutes per year. This is close to the accurate modern value of 50.3 minutes or seconds, sorry, per year. So arc seconds. So that's really cool. He made some measurements like that. He established the magnitude system for describing the brightness of stars. He called the brightness stars first magnitude and then worked downward through second, third, fourth, and fifth magnitudes, all the way down to the faintest stars he could see, which were labeled sixth magnitude. The more quantitative magnitude system that is used by astronomers today, that's based on Hipparchus. So Hipparchus set up a lot of, a lot of the current astronomy a lot of the current astronomy units and measurement styles are actually very old. They go back to the time of Hipparchus, so that would explain why it might seem a little bit different or weird, but astronomy is really old. He computed a more accurate distance to the moon, although the original work of Hipparchus is lost. Like so many works of Greek astronomy, a later commentator stated that Hipparchus found the average Earth-Moon distance to be roughly 70 times the Earth's radius. The actual average separation is 60.5 Earth radii. So not bad. He was pretty close. These guys were good. The Greeks were really good. He measured the length of the tropical year with an error of less than 7 minutes, despite having such an accurate measure of the length of the year available, the Roman pontifices still botched their calendar. The observations of Hipparchus were the basis of the Ptolemaic model for the universe, which dominated Western astronomy for more than 14 centuries. Oh my God. Oh wow. So, yeah. Next is Ptolemaic astronomy. I I didn't realize that it was around. I mean, I guess that would make sense. I mean, this is only still BC. So for the next 14 centuries, Ptolemy is what ruled. Look at Ptolemaic. Um, Let me see your comments. I even saw F-22 stealth fighters fly overhead during the eclipse. Oh, good. I saw two fighter jets chasing something. I saw two fighter jets chasing something that split into two things. True story. Wow, I have a weird. I was driving up a two-lane road and saw something cross the road behind me. I have a feeling that this will be the best time of my life. Says a lot about the Greeks. Yeah. 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 No, they were really smart. So Ptolemaic astronomy, let me show you this geometry for the Ptolemaic astronomy. So there it is. It was actually pretty complicated. So they put the Earth, a planet moves at a constant speed around the center of its epicycle, while the center of the epicycle moves at a constant speed along the deferent. So they had to come up with all of this to do the Ptolemaic astronomy. The combination causes a model planet to move in a loop-the-loop motion. So because, all right, let me just read. It'll become clear. Restop spam. He's not spamming Death Dragon. He's all right. You're the one who's spamming sometimes, if I may say so. He's not spamming. He's saying amazing machine. Thank you. Antikythera mechanism. Oh, wow. Yeah, see, I didn't know what that is. To be able to build a mechanical computer thousands of years. Yeah. Okay, perfect. Yeah, I had no idea about that. Claudius Ptolemaeus. Ptolemaeus. I don't know if I'm saying that right. Claudius Ptolemaeus, called Ptolemy for short, thank God, lived and worked in Alexandria, Egypt during the mid-century AD. The scanty details that we know about his life come from his surviving astronomical books, his main work, which Ptolemy called Mathematique Syntaxis. It's okay, Death Dragon is better known by the name applied to it in the Middle Ages, the Almagest, a name that comes from an Arabic phrase meaning the best. As you might guess from its flattering nickname, the Almagest was the most highly regarded astronomical work in the Western world from the time it was written until the 16th century. The main portion of the Almagest, I don't know how you say it, is devoted to a geometrical model that describes the motions of the stars, sun, moon, and planets as seen from Earth. Before going into detail about Ptolemy's model, let's briefly review the motions of celestial bodies that he was attempting to explain. Stars move in diurnal circles about the celestial poles with one complete circuit, requiring one sidereal day. The stars are fixed in position relative to each other. This is only approximately true, but the relative motions of the stars are too gradual for the Greeks to have discovered. No, it's all good. These are interesting inputs. Thank you. Need to slow down. They found a chunk of copper with what looked like gears. They x-rayed the chunk and saw gears and cogs in the chunk. I'm glad. Yeah, no, it's feel free to talk to each other about these interesting things. So Ptolemy came up with this particular model Sun, moon, and planets as seen from the Earth. It was found in a shipwreck over 2,000 years old. Wow. So these were the review of the motions. Stars move in diurnal circles about the celestial poles with one complete circuit requiring one sidereal day. The stars are fixed in position relative to each other. This is only approximately true, but the relative motions of the stars are too gradual for the Greeks to have discovered. The sun moves eastward relative to the stars along the ecliptic, which is tilted at 23.5 degrees relative to the celestial equator. The average rate of motion is roughly 1 degree per day, but this varies over the course of a year. The moon moves eastward relative to the stars along a path close to but not identical with the ecliptic. So all of this is part of Ptolemy, what he was proposing. The average rate of motion is roughly 13 degrees per day, but this varies over the course of a month. The planets Mercury, Venus, Mars, Jupiter, and Saturn usually move eastward relative to the stars along a path close to the ecliptic. Sometimes, however, they reverse course and move westward. An example of the prograde, eastward, and retrograde motion of Mars is shown in an earlier figure. So Ptolemy's job was made unnecessarily complicated by the erroneous assumptions that he made. First, he assumed that the Earth was stationary at the center of the universe. In other words, the Ptolemaic model was geocentric, Earth-centered, rather than heliocentric or sun-centered. Second, he assumed that celestial bodies moved in perfect circles at constant speed. This doctrine of uniform circular motion can be traced to early Greek philosophers such as Pythagoras and Plato. They believed that the heavens were perfect. Oh, that's right. So to say that they were not uniform circular motion was also a really big deal because basically the thought was that the heavenly bodies were completely perfect. They believed that the heavens were perfect in contrast to the obviously imperfect earth, and that heavenly bodies must therefore move in circles which were regarded as a perfect shape at a perfectly constant speed. Given these assumptions, so I think they made their lives very difficult because once you have these assumptions, you have to come up with a very complicated type of model to try to explain the motions that you were seeing. And things like that to kind of make it match up with your observation. Given these assumptions, explaining the apparent motions of the fixed stars, because they thought that the stars were fixed, the stars can have a little bit of motion, but they thought that those were fixed, couldn't really tell, was they thought that explaining the apparent motions of the fixed stars was easy. Ptolemy assumed they were affixed to a rigid spherical shell which rotated from east to west about the celestial poles, completing one rotation every sidereal day. Explaining the apparent motion of the sun was more difficult. How could the non-uniform motion of the sun along the ecliptic be reconciled with the dogma of uniform circular motion? Ptolemy followed the example of his predecessors by using a concept known as the eccentric. The sun, Ptolemy assumed, moved along a circular orbit at a constant speed. However, the Earth was offset from the orbital center by a short distance. Oh. This small offset was referred to as the orbit's eccentric. As the sun moves along the orbit at a constant physical speed, its angular speed as seen from Earth is greatest when it's closest to the Earth and the smallest when it's farthest from the Earth. Ptolemy found that when he displaced the Earth from the orbital center by roughly 4% of the orbital radius, he could reproduce the observed motions of the sun with fair accuracy. So, yeah, they recreated the battery. I feel like my brain is going to explode. Oh, why? Around 2,000 years old. They recreated the battery and poured citric acid into the container, and it produced a low charge. That's a common feature of coming in these lives. My voice is cracking. It's either winter cold or early. Oh, do not get me started with history. I love history. But how cool is this? They were working so hard. Ptolemy and company were working really hard to make the sun work out its observation. So he moved the Earth 4%. Although the eccentric can describe an angular speed that varies with time, it cannot describe retrograde motion, in which the angular speed of a planet actually changes sign. We're in some sort of retrograde right now, according to astrology. So, apparently that's a whole thing right now. Rather than simply slowing down and speeding up, Ptolemy explained retrograde motion of a planet by using an epicycle. So look at this. This epicycle business is not an easy geometry at all. And Copernicus later on, did away with it and said that actually the sun was at the center. Then that kind of solves everything. But of course, they had a lot of resistance towards that because of religious reasons as well. I subscribe just to let you know. Oh, thank you. Yes, please do. Please have your whole family subscribe if you could. Everybody like, subscribe, share. Please. Thank you so much. So, I'm just going to tell you that the epicycles, we had to, I think students are still kind of made to do this stuff just to appreciate that the epicycles were so complicated. I first liked and then subscribed. Thank you. Thank you so much. The epicycles are not easy at all, but that's what they needed. Oh, God. Okay. So Ptolemy explained retrograde motion of a planet by using epicycles. In the epicyclic model, a planet travels at a constant speed around a circular path called an epicycle. At the same time, the center of the epicycle Yay. Hi, Navsath. Good morning. How are you? My middle name is Stephen, but spelled like this. Oh, with a V. It's okay, Death Dragon. Don't time him out. Let him be. Navsath. Don't spam too much for our sake, because Death Dragon will ban you probably. But happy to have you here. Thank you. The center of the center of the epicycle moves at a constant speed. Look at this. This center of the epicycle. So they were doing such complicated math. The complete Ptolemaic model for a planet's motion, including the equant. Look at that. There's even something called equant. What happened? Oh, nothing. We're just discussing Ptolemaic astronomy. So the combination, the center of the epicycle moves at a constant speed around the center of a larger circle called a deferent. So there's a lot going on. The combination of an epicycle and a deferent can produce retrograde motion. So they got retrograde motion worked out. In order to, with this complicated type of stuff. Suppose the planet moves counterclockwise at a speed v around its epicycle, while the center of the epicycle moves counterclockwise at a speed w around its deferent. When the planet is at the outside of its epicycle, its speed relative to the center of the deferent is v plus w. When it's at the inside of its epicycle, its speed is v minus w. So thus, if w is greater than v, the planet is actually moving backward or in retrograde when it is closest to the center of the deferent. A typical path traced out by a planet on an epicycle, we just looked at that, by fiddling with the sizes of the eccentrics and epicycles and by playing with the relative orbital speeds of epicycles and deferents, Ptolemy could get a fairly good fit to the observed motions of planets on the celestial sphere, but not quite good enough. His models were unable to match the observations exactly. Eccentrics, deferents, and epicycles were ideas that Ptolemy had inherited from previous Greek astronomers. However, in order to match the observations with the necessary accuracy, Ptolemy introduced a new device called the equant. Oh my God. So it gets even more complicated now. I'm a little boy. I did that as a little boy, but my parents corrected me. It's spelled Stephen in the Bible. Welcome, I'm 11, I'm a little boy, but nice, smart, but strict. He is very strict. It's Baji. Death Dragon is very strict, everybody. But the other day, Death Dragon, I must thank you. I know you get excited to ban people, but the other day he did save me from someone very dangerous. So thank you, Death Dragon. He was he was there was actually someone who was actually causing trouble, and Death Dragon gave him a warning a couple of times, and then he was that's it. And we were like super shocked. We were having an innocent chat, and there was this one person, and Death Dragon just brought down his hammer. So I'm afraid, honestly, of Death Dragon. What are you doing? Oh, okay, all right. Nope, now Sat. What? Oh my God! Now, oh my God! Are you serious? Did you ban now, Seth? I'm about to go Ultra Instinct or Super 24-hour ban? Can you reduce it, please? Let him come back in 30 minutes. You're gonna get my channel closed down with this rate of strictness. Nevertheless. So Ptolemy now even has equants, another whole thing to make his thing work, his model work. So I know. Now, Seth, just time him out for like 5 minutes. That's enough. That's enough punishment for somebody who didn't say anything creepy. Not that I saw anyway. If I don't see it, it didn't happen. I'm just like, it's all good. We're desperate here. I'm gonna choke. I reduced it. Okay, what is it now? 24 years? I just can't. I can't. You'll end my YouTube career, Death Dragon. Okay, so Ptolemy was working. I was mad, sorry. Yeah, Death Dragon does have anger issues. We have an anger issue. My friend here has anger issues. Please just keep that in mind, everybody. Okay, so, let's skip Ptolemy for the rest of this because Ptolemy was working extremely hard to make the geocentric model work. And I'm tired of it already. Don't be sad. Don't be sad, Death Dragon. Um, you know you're loved on the chat. Everybody likes you. You're banning people for too long though. Give them a smaller. Give them a smaller timeout. Everybody respect uses my bad universe. Yeah. So moderation in punishment is good. So Ptolemy, in other words, worked extremely hard to make this geocentered model work. There were a lot of different reasons, like heavenly bodies having to be perfect and religious reasons like that, and it was actually kind of a difficult model. Now comes Copernicus. Are you ready? I'm ready. I'm ready for Copernicus. So we're going to kind of skip the rest of Ptolemy. And we'll just go straight to Copernicus, which, of course, Copernicus did not come in a hurry. Remember, the Ptolemy, or what? Really? Ptolemaic astronomy? Yeah. So Ptolemaic astronomy was around for 14 centuries. That is 1400 years, Death Dragon. You know how you ban people for 1400 years sometimes? It's kind of like that. So, because Ptolemy was born in, wait a minute, where is his year? Mid second century AD. So it might have been shortly after Christ. But basically, so like 180, 280 versus 1473. Copernicus was born. Oh yeah, love Galileo, of course. Yeah, love him. Oh my gosh. Absolutely. Copernicus was born in 1473. So that is 1400 years after Ptolemy has done all that stuff. And the Ptolemaic model of the geocentered model, which was very complicated, had lasted for 1400 years. So quite a long time. The Polish astronomer Nicholas Copernicus, 1473 to 1543, was the first scientist since antiquity to advance a heliocentric model for the universe. Isn't that so sad, though, that Aristarchus basically had it? Like, he was in the right track. Like, he did a lot of things really well. But then Ptolemy came and kind of made everything geocentric. And it's bizarre because it lasted for 1400 years. It's almost like, who knows? Like, if that hadn't been the way, then who knows? But I just think that the misinformation lasted for so very long, though. It's kind of blows my mind. The Polish astronomer Nicholas Copernicus was the first scientist since antiquity to advance a heliocentric model for the universe. Copernicus was a Renaissance man, metaphorically as well as chronologically. In addition to studying astronomy and mathematics, he also traveled to Italy in order to study medicine and law. Look at that guy. He studied everything. Be like Copernicus. After taking minor orders in the church, he served in a variety of administrative positions. His work for the church left Copernicus with enough time to make astronomical observations and work out his heliocentric model in detail. By the year 1514, Copernicus was circulating a brief manuscript about his ideas among his friends. Oh, I know about this manuscript. Oh, this is going to be quite something. The grand summary of his work, the book, De Revolutionibus Orbium Celestium, on the revolutions of the heavenly spheres, was not published until Copernicus was on his deathbed in year 1543. Who is Galileo? Is he like Neptune, Poseidon, Thor? No, Galileo is a real guy. We will talk about him. He's an astronomer. So Galileo Galilei is a real Italian person who contributed a great amount to astronomy and, yes, developed the first working telescopes. I actually, Galileo in this book is called the first modern scientist. So, amazing, amazing person. I actually saw the spot in Rome where he was going in and out of when he was made to go to prison, where he like appeared for his case and stuff. It was part of my tour, actually. So, really cool. Kind of a scary story of his life, but we will absolutely get to Galileo. He's one of my favorites. So, absolutely. Hold on for Galileo. We're still on Copernicus. Copernicus is extremely important, of course, because in the more well, I don't know if I can call it modern, really. 1400s is not exactly modern, it's still very old. But in the 1400s, he's the first person to not only kind of put the sun back in the center, heliocentric model, work on it, but also he published on it. That was a really, really, really big deal. So, because even if you say thought something, believed something, wanted to do something different than the geocentric model, to be able to publish on it and then, not be in trouble was a very big deal. I think he did have some issues, of course, himself, but he studied Jupiter and its big visible moons and Saturn and its rings. Yes, absolutely. It was actually a very big deal that he found moons of Jupiter, meaning that we were not that special. Like Earth has a moon, but Jupiter has moons too. Like that was something very special. And the Saturn and its rings, that also had some importance in, like, I think it was something like the heavenly bodies were not as perfect as people wanted them to be, etc., etc. And yeah, showing that other planets had moons. See, one of the things with Earth was because we do have a satellite, we do have one thing going around us, which is the moon. It kind of gave people that encouragement that maybe the Earth is in the center. But then to show that other planets also have moons, that the Earth is not that special. Planets can have moons is a very, very big deal. So Galileo was being very revolutionary when he found that some other planet also had moons. There was a big significance with that. So thank you, Stephen, for this very helpful comment. Historically, saying that something other than the Earth has moons had heavy consequences. It was not just a statement of fact. It was something that he got into a lot of trouble for. But that was the truth. So, yeah. So the most radical aspect of the Copernican model was its insistence that the sun, not the Earth, was at the center of the solar system, and that the Earth was both rotating about its axis and revolving about the sun. The Copernican model, however, also had conservative aspects. For instance, Copernicus wholeheartedly embraced the dogma of uniform circular motion, so he kept it all uniform circular. One of his proudest claims for his heliocentric model was that it eliminated the need for equants. However, to match the observations, it still needed eccentrics and epicycles. The Copernican model, although it retained eccentrics and epicycles, was conceptually simpler than the Ptolemaic model in many aspects. In the Copernican model, retrograde motion of the planets is accounted for by the fact that inner planets move faster along their orbits than the outer planets do. Thus, as an inner planet, such as the Earth, overtakes an outer planet such as Mars, the outer planet undergoes retrograde motion as seen from the inner planet. This is demonstrated graphically right here. See, lots of circles. So he actually kept the uniform circular motion. Wow, that's pretty conservative, but Copernicus was still being very... You mean, so the moon doesn't have a moon? I wonder why nothing orbits the moon. Like, is there just a limit to what size planetary body or mass has an orbiting body? Um, I mean, there could be like rocks and stuff. There's nothing. Yeah, the moon. I guess the moon is kind of, well, no, it's not. It's not the case that the moon is too small. Our moon is actually a very big moon, so it could have. Did anyone see the second moon we had for 2 months? No, but I read about that. Yeah, no. So it's not the size. It's not the size. Nope, that's not it. Anyway, we'll keep going. Is so let's see what was the sentence? Because so I was saying earlier, I think before you came, Reese, that you know, the Earth has only one moon and well, one main moon, and that's kind of rare. Most planets, I think every other planet in the solar system pretty much has multiple moons. And the nice thing or the special thing about us though is our moon is one of the largest moons in the solar system. So yeah, no. The moon could have a moon probably, but no, it doesn't. It doesn't. But I guess, if there was, it's not that the moon could have a moon, it would be our moon. You know what I mean? Like it would we would be the, say if there is, so the moon is pretty close to us, right? If there was another moon's moon, that moon would be more affected by us, the Earth, than the moon, because the Earth is the bigger thing by a lot. So it wouldn't really go around the moon, it would go around us. You know what I mean? Our moon is unusually big in relation to the Earth, isn't it? Our moon is one of the biggest moons. So if you look at all the moons of all the planets in the solar system, our moon is one of the bigger ones. Yes. It's not so much to do with the Earth size, but the fact is, like the moon might even be just a chunk out of the Earth, right? Most likely. Like when the solar system was forming, for all we know, when the Earth wasn't cooled down yet and the rock and stuff had not formed, for all we know, the moon is just a chunk out of the Earth or whatever. And the moon goes around the Earth because just how everything worked out, the moon is close to the Earth. So basically, if the moon went around the sun, then it would be a planet. But because it goes around us, it's a moon of us, which is, we're a planet, so the thing that goes around us is called a moon. And if there was, say, another thing, then, and it was close enough to the moon, then it would also be close enough to us, and we would probably just have a second moon, like most other planets do. Most other planets, I think even Mercury has like 3 moons, doesn't it? So it's actually kind of a bummer that we only have the one moon. Did anyone see the second moon? It's interesting how the moon can block the sun to produce an eclipse. Yes. Our moon is unusually big. Well, our moon is one of the biggest moons, yes. The only thing I can think of is that the first time I heard of this, I had a panic or something. Oh. Heard about what? So, yeah. Strange, isn't it? There's a theory that an asteroid struck the Earth and the moon was formed from the impact. They called... So what dictates how many moons a planet has? I don't think there is a law of how many moons a planet can have. It's just how historically this solar system came to be, Whatever, it could be the asteroid thing that Stephen is saying, or it could be, some sort of something that makes another separate rock, basically. And depending on how the gravity lines up, you could have it be orbiting Earth or a different planet or whatever. We just happen to have this thing be our. And you know, at first, basically my thought would be that Earth actually cooled down, right? Everything was much more like molten lava, more liquidy. Like Jupiter, for example. The first time I heard about this, I thought it was a joke. Heard about what? So you know, for example, up to Mars we have rock. So we are the inner planets. Mercury, Venus, Earth, and Mars are rocky planets. It's rock. That just means that we've cooled down enough, and we're also small enough where we cool down enough to make rock. After that, there is no rock. You know, Jupiter onwards are gas giants. Those planets have not cooled down. And if chunks out of them go out, so another way to think about it is a moon is, you know, what type of moon is it? Sometimes a moon is generally obviously a lot smaller than the planet it's around. So that might help it to become sort of a different like material maybe than the planet. Like Jupiter has a ton of moons. So I don't think there is really a law that dictates. Nothing really dictates how many moons a planet can have. It's just sort of the history of how things developed. So yeah. Anyways, it just so happens that we have the one moon, and it's a rather large moon. So that's kind of cool. And it's so pretty. I kind of want a job now to make some money. Okay. That's very nice, Death Dragon. I like your ambition. I also was like this. I also wished that I had my own money when I was little. Inferior planets are those with orbits smaller than the Earth's orbit. That is Mercury and Venus. So Mercury and Venus have smaller orbits and they're closer to the sun. Superior planets are those with orbits larger than the Earth's orbit. Mars, Jupiter, and Saturn were the superior planets known at the time. Copernicus, during the time of Copernicus, the planets Uranus and Neptune, and the dwarf planets Ceres, Pluto, Haumea, Makemake, and Aries were not discovered until after the invention of the telescope. So they only knew until Saturn. And both Jupiter and Saturn are gas giants, by the way. They have not cooled down. See, they're pretty far from sun, so you might expect them to have cooled down and made rock, but they're too big, so they have not cooled down, and they're still gaseous. They're gas giants. So that's another thing, just a fun fact for you guys. Not every planet is like ours. Earth has rock. You know, we can walk around on it. It's very, in that sense, it's very special. And it has an atmosphere that lets us breathe in everything. It's pretty amazing. So in the Copernican model, the Earth is in motion around the sun. Thus, for an earthly observer, the positions of planets are measured from a reference frame that is co-rotating with the Earth-Sun line. It is particularly useful, as we shall see, to measure the position of planets on the celestial sphere relative to the sun. Some special positions of the superior planets relative to the sun are shown in this figure. A position occurs when the Earth lies between the sun and the superior planet. That is, the sun and the planet are 180 degrees apart on the celestial sphere. Conjunction occurs when the sun lies between the Earth and the superior planet. Quadrature occurs when the sun and the superior planet are 90 degrees apart, as seen from the Earth. So all of this stuff was Copernican. We will skip a little bit because I think we sort of get it. It's getting there. It's making good progress. I was so upset when Pluto was made into a dwarf planet. Mind you, I'm 59. Yeah, Pluto losing planet status is a pretty big disappointment. That's for sure. Yeah, but you know what? Pluto doesn't care. whether it's a dwarf planet or not. And I think Pluto did not lose its spot in significance in astrology, for example. So in astronomy, it's a dwarf planet, but in general, Pluto still just does its thing. Doesn't really matter how we categorize it. So, but yeah, I mean, Pluto has a crazy orbit. So it's, in that sense, it really is not the same as the other planets. Sorry, but yeah, having the nine. Oh my gosh, yes. Pluto got death dragoned. Pluto, your orbit crossed Death Dragon's limits. I know, Pluto has been banned for 2400 years. See, everybody's enjoying you, Death Dragon. They think you're funny and fun. Okay, lots of things by Copernicus. Now we will read about our favorite, Galileo. Oh, look, here's a table of the planetary orbits. So we have Mercury, Venus, Earth. Mercury's sidereal period is 0.2 years. So in our year, Mercury's orbit is 0.2 years. Venus's is 0.6. Ours is 1, of course. Mars is 1.8. Ah. Ceres is 4.5. Jupiter is 11.86 years. Saturn 29.44. Wow, Saturn. Uranus is 84. Goodness, Neptune is 164 years, is in orbit. Pluto, Mr. Pluto, is 247 years. Haumea is 283 years. Makemake, 306. Aries is 559. Or Eris. Maybe Eris. Maybe I'm saying that wrong. Eris. Pluto got death dragoned. Pluto is still a dog in my heart. Once upon, Pluto was inside the orbit of Neptune. Aww. Yeah. All right, you guys, are you ready for Galileo? You got Pluto? Oh yeah, we're going to talk about this. This is going to be awesome. It's going to be awesome. Galileo, Galilee. Both the Ptolemaic and Copernicus, so Galileo is called the first modern scientist. Both the Ptolemaic and Copernican models could explain the observed motions of the sun, moon, and planets on the celestial sphere. Why then should one believe that the Earth is in motion rather than the sun? We know now that the Earth does orbit the sun rather than vice versa, but direct experimental proof of the Earth's orbital motion was not provided until the 18th century, nearly 2 centuries after the death of Copernicus. Nevertheless, the heliocentric model came to be accepted without direct proof. This was partly because of its elegant simplicity. The motions of the planets are less complicated in a heliocentric model than in a geocentric model. This is an application of the general principle often referred to as Occam's razor. In its typically quoted form, Occam's razor states that the simplest description of nature is most likely to be most nearly correct. In other words, unnecessary complications should be shaved away from a theory. Of course, when using a razor, it is important not to cut too deep. Albert Einstein is said to have rephrased Occam's razor in the form, everything should be made as simple as possible, but not simpler. What's the direct proof of what? The New Horizon probe was so cool when it finally got pics of Pluto. Yeah, going as far as being able to get pictures of Pluto is a pretty big deal. Pluto is not close, it's very far. Have you seen the Voyager 1 Earth in the sunbeam? Oh, I see. I think you're talking about the heliocentric model being... yeah, hopefully, I I'm not sure. I don't remember what was the first direct proof um, of the heliocentric model, if that's what you're asking. Um, I don't know. Maybe it could be. I just like so much has happened since this time that we're discussing that I'm just not sure what was this first. Like we see things with you know, spacecraft now, so that could be it. I don't know. We'll see. In addition to the aesthetic appeal of the heliocentric model as opposed to geocentric. Yeah, that's what I'm trying to remember. I don't know or I can't remember. I probably read this, but I can't remember what the first direct evidence was. Yeah, I don't know. Because we're still discussing stuff that's pretty old. I just don't know. I just don't remember what the direct was. In addition to the aesthetic appeal, so basically at this point, they're still kind of just, they're taking the simpler theory and, you know, slowly adapting to that. In addition to the aesthetic appeal of the heliocentric model's relative simplicity, compelling indirect evidence for heliocentrism was provided by the telescopic observations of Galileo Galilei. So, Galileo gave a number of very important telescopic observations. We will read about those. Galileo is sometimes called the first modern experimental physicist. Instead of relying purely on the pronouncements of Aristotle, Galileo tried to understand how nature works by carrying out experiments such as swinging pendulums back and forth and sliding weights down inclined planes. So all of that stuff is from Galileo. And so basically, Aristotle had given us a bunch of theories, sort of like how theoretical physics works even now. Like you can theorize something, but until you prove it with experiments and really probe it, not just probe it with experiments and really, measure and things like that. It's not really an experimental science, and physics started to become much more of an experimental science from the time of Galileo, and thanks to Galileo. It's not just about theorizing something and saying what should be and how things should be, or, coming up with some elegant thing that you like that you can't really prove, though that type of thing was fine. It was more of a philosophical approach, honestly, by people like Aristotle, right? But Galileo is considered the first modern scientist because he kind of started to actually probe it. Like probing space, with telescopes, that's much, much more modern and much, much more in line with what we would do now. So, yeah, I remember the Voyager 1 and 2 probes when they passed the outer solar system and the Viking landers on Mars. Yeah. So, anyways, Galileo, let's see. Although Galileo did not invent the telescope, he was among the first individuals to use a telescope as a scientific instrument. I don't know, I actually can't remember who the first person to build a telescope is. I think he's the one who greatly improved it, maybe. Instead of relying purely on pronouncements of Aristotle, Galileo tried to understand how nature works by carrying out experiments such as swinging pendulums back and forth and sliding weights down inclined planes. Although Galileo did not invent the telescope, he was among the first individuals to use the telescope as a scientific instrument. The actual inventor of the telescope may possibly have been a Dutch optician called Hans Lippershey. In October 1608, Lippershey applied for a patent on what he called a Kitschker, or looker in English. The patent was denied by the Dutch government, however, on the grounds that many other persons had a knowledge of the invention. Indeed, news of the telescope reached Galileo in Italy as early as May 1609. Soon thereafter, he built several telescopes, each superior to the one before. So maybe he didn't come up with the idea, but he built some of his own and better ones. Although Galileo's telescopes had apertures of only an inch or two, they provided Galileo Hans Lippershey. Yes. Ooh, very nice. Galileo was ridiculed by the church for his work. Yes, Galileo was more than ridiculed. He was attacked by the church and thrown into prison, if I'm not mistaken. But yes, we will get there. The patent was, we just read that. Although Galileo's telescopes had apertures of only an inch or two, Death Dragon, what is it? Okay. They provided Galileo with many important observations. Galileo, knowing the potentially revolutionary impact of his discoveries, rushed into print in March 1610 with a pamphlet entitled Sidereus Nuncia, Starry Messenger. Many of Galileo's observations were startling to his contemporaries. So these are... Hi, guest not found. Guest not found is also a friend. Death Dragon, please calm down. Thank you for being here. So these are Galileo's observations, if you guys are ready. They are remarkable. The moon, so Galileo built some of his own telescopes, and each one was better than the last. And he used them and made some remarkable observations. And these are as follows, and just pay attention because these are amazing. So, and all of these were sort of like a hit on the church. Like the people at the time did not want to believe this at all. They didn't want to accept it. It was very offensive. So Galileo was being like a revolutionary by saying all of this. So the moon is not smooth and perfect. The moon, being a heavenly body, was expected or thought to be perfect and like amazing and smooth and all this stuff. So finding sort of like faults of the moon was a big deal. It was a really, really big deal. Anyways, the moon is not smooth and perfect. Instead, as Galileo wrote, it is uneven, rough, and crowded with depressions and bulges, and it is like the face of the earth itself, which is marked here and there with chains of mountains and depths of valleys. In other words, there is not a vast difference between the earth's surface and that of a celestial object, namely the moon. So he's saying that the moon, which is a heavenly body, yes. Deep breaths are good. The moon is a heavenly body and it has imperfections. That was huge, just huge. Next, the Milky Way, the nebulous band of light that extends around the sky, actually consists of numerous faint stars. To whatever region of it you direct your spyglass, Galileo wrote, an immense number of stars immediately offer themselves to view. So the Milky Way had all these more and more stars that he could see. That was something next. And then next bullet. Through a telescope, stars remain unresolved points, but planets show as disks. As Galileo put it, the planets present entirely smooth and exactly circular globes that appear as little moons. Unfortunately for astronomers, even the nearest stars are too distant to be resolved with conventional telescopes, even telescopes much larger than Galileo's. So like, all that stuff about fixed stars and things like that, he's going against that. The planet Jupiter has 4 large bright satellites. So the same 4 moons that, what's your name, Stephen? The same 4 moons that Stephen might have seen from his backyard, Galileo saw all of those years ago. And discovering the moons of another whole planet was a huge blow. It meant that the Earth wasn't special in that we had a moon. going around us, making us so special. No, other planets also had moons. And if they were, he obviously probably saw the biggest ones first because Jupiter has lots of moons. That was a big deal. So the planet Jupiter has 4 large, bright satellites. Although Galileo called these satellites the Medicean stars in honor of Cosimo de' Medici, Grand Duke of Tuscany, later astronomers named them the Galilean satellites. The individual names of the 4 Galilean satellites are Io, Europa, Ganymede, and Callisto. Yay! Yay, Stephen. Have you seen these 4? Io, Europa, Callisto, and Ganymede? Ganymede is Ganymede. Callisto, you got it. Io is Io, like you said. Europa is like Europe, but with an A in the end. So yeah, the Galilean satellites of Jupiter. So saying that another planet had moons was a big deal. The Galilean satellites of Jupiter were an indirect piece of support for the Copernican system. One objection to a heliocentric model was that it required multiple centers of motion. The fact that the Earth was a center of motion, as in we had a moon, then the Earth goes around the sun, so that's another center of motion. This was an issue people raised with the heliocentric model. So, yeah, Io is the innermost. Okay, that's okay. Yeah, thank you. So, one objection to the heliocentric model was that it required multiple centers of motion. The Earth went around the Sun, while the Moon went around the Earth. This was regarded as more complex than a geocentric model in which everything goes around the Earth. However, Galileo provided clear evidence that there had to be multiple centers of motion. Obviously, the Galilean satellites were going around Jupiter, regardless of whether Jupiter was going around the Sun or around the Earth. So by the end of the year 1610, Galileo made another telescopic discovery that further undermined the Ptolemaic model. He found that Venus went through all the phases that the moon did, from full to new. Wow. Moreover, he found, so the phases of Venus, goodness, which is only, I think that's only possible with a telescope, because you can't really see that with the naked eye. Moreover, he found that the angular size of Venus was smallest when it was full and largest when it was a thin crescent. The phases of Venus, illustrated by Galileo in his later work, I don't know how to say this, 1L Saggiator, shown here. Here's the, where are you? Here's the Copernican versus Ptolemaic. And where is, phases of Venus right here. So the phases of Venus look like that. So the crescent one is actually bigger. Goodness. So Ptolemy, in his geocentric system, had the task of explaining why Venus should always lie within 46 degrees of the sun if the two bodies were on independent orbits around the Earth. Ptolemy managed it by saying that the center of Venus's epicycle always lies directly between the Earth and the Sun, and that the epicycle is big enough to subtend an angle of 92 degrees as seen from the Earth. The geometry of this situation requires that we see primarily the nighttime side of Venus, that is, the side away from the Sun. In the Ptolemaic system, then we would always see a new or crescent phase for Venus. Galileo demonstrated, however, that we see gibbous and full Venuses, as well as crescent and new Venuses. This is easily explained in the Copernican system, as shown here. You saw that. In the Copernican model, the sunlit side of Venus is turned toward us when Venus is at superior conjunction. This is when Venus is at its greatest distance from Earth and hence has its smallest angular size. Wow. Conversely, the nighttime side of Venus is turned toward us when it is at inferior conjunction, when it is closest to Earth and has its largest angular size. Can I please put now South in timeout for 10 seconds or 1 minute? It's okay, let him be. So, okay, thank you. So yeah, that was it. Those are the biggest things for this topic. From Galileo, the phases of Venus was a big thing too. And along with all the other things, discovering the moons of Jupiter is huge. Discovering the imperfections on the moon is huge. Discovering that, you know, the stars, there's like lots of them. You can't resolve them very easily. They kind of like flicker and stuff. They're faint and it's numerous. It's not like there's just the stars that we see or like the fixed stars, but there's like more and more and more that you can't even see, but then, you know, becomes visible based on how well your telescope is or something. So it's almost like, I think the point about that is that it wasn't that just this perfect dome of fixed stars really. Actually, there were more. Until the Russians put probes on Venus, people thought Venus was exactly like Earth. Yeah. Yeah, I mean, Venus is the one that's closest to the size of the Earth, and it's not too far from Earth. And, but yeah, its atmosphere is poisonous. I was saying earlier, I don't know if it was today or yesterday, that I would pick Venus to live on over Mars, but its atmosphere is too poisonous. But anyway, next would be Kepler's laws of planetary motion. So in this chapter, the next part is Kepler's laws. I think we will save that for next time. I just wanted to give you guys an introduction to how astronomy kind of came a very long way. We can just chat for a while here today and save Kepler for the next time. What do you guys think? What did you think of this? The whole Ptolemy, Copernicus, Galileo. What do you think, Death Dragon? What do you think? What did you think of all the astronomy that we just learned? It's late, so we will continue this another time. But I thought this was pretty cool, huh? The atmosphere is also so thick, the pressure could destroy a lander on Venus in 2 hours. Indeed. Yes. 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 I actually don't know, but I'm sure you read that somewhere. But yeah, so we have Kepler's laws of planetary motion. We have proof of the Earth's motion, rotation of the Earth. Yeah, we have these. So not a bad chapter. Almost. We covered, I think, some of the more interesting parts today. Steven says, good night. Good night. Good night to Virginia. Good night, everybody. If you want to stay and chat for a bit, I'm still around. But thank you for joining. Thank you for being here. Thank you so much. Is it? What time is it? It's 2:10. Okay. This is going to be a short live. Usually our lives go for like Sometimes we're live for like 3-4 hours. So, um, oh, I love it. Thank you, Nasat Nasat. Thank you so much. I love the night sky emoji. Sweet dreams. Thank you. Sorry about the timeouts. I think we just have a very strict mod. Thank you. Thank you for being here. Thank you for sticking around for the chat. Thank you for being on the live. Thank you for contributing to all the chat messages. Lots of astronomy. Lots of astronomy chat messages, so thank you so much for that. It was your cats that caught my attention. My 3 cats are all gray tabbies like yours. Yeah, I know. We reel people in with the kitty cats and then we teach them physics and astronomy. That's pretty much the channel, Stephen. Thank you so much. And yeah, have a great night with your kitty cats. We're so happy to hear that you have 3 kitty cats as well. Thank you for taking care of them. Death Dragon says, don't go, please. Okay, well, we can stay for a while. We can chat, Death Dragon. Oh, whoops. You know what, Death Dragon? My phone's gonna die. It's at 1%, so let me put it on charge. Death Dragon, you don't want us to leave? But I thought you were banning people. I thought you were banning everybody. So, Death Dragon, what are you doing tomorrow? You gonna eat turkey or what? A lot of turkey? No, not anymore. Okay. Dragon is more friendly now. This was fun. This was so much fun. This was a lot of fun, guys. Here, I'll get my laptop and chat without talking because I need to take some deep breaths myself. I have a... I need to catch my breath. Thank you. Thanksgiving. Mr. Kitty is a stray that adopted up. Osha and Luna were shelter rescues. Let me see your comments. Mr. Kitty's straight. Going to my papa's house and my booby's house. Bobby's house. Thank you for reading and explaining. Thank you, Heike. How are you, Heike? Everything good? I have to go to my sister's house and mend her laptop, microwave, Nintendo Switch, erect a cabinet, and install a light fitting. What? She doesn't want much. Can I ask when you're online? Yeah, we go live almost every day, Stephen, at night. And some days we also go live in the afternoon. So since you're in the US, I can just tell you because I'm in Boston, so, you know, our time zone is like the same, East Coast. So pretty much I go live, like my biggest live is Friday night live. But pretty much I'm going live most days now at night. So I started like whatever time, 11 p.m., 11:30, midnight-ish time. But then some days if I want to like go to bed early, I also get started like in the later afternoon, in the evening. Yeah. Thanks. I'll keep my eyes open. I've been to Boston. Yeah, if you get the notifications to come on, it should notify you when we're going live. But we go live most days now. We might just take like a day here and there off, but most days we go live. Especially at night, but also afternoon, evening time. Probably not in the morning, not a morning person. So if I'm live in the morning, it's probably the very small hours of the morning, like early morning, like now. Probably not like 10 a.m., 11 a.m., noon. Well, sometimes we go live around noon if we go live in the afternoon. But yeah, those are the times. Thank you for asking, and thank you for joining in the future as well. Thank you so much. Appreciate. Whoops. Appreciate it. I'm charging my phone over here, so that's why. Stupid question, how do I activate? So I think you have to like press on the bell icon. So after you subscribe, there might be another button with a bell icon, which tells you notifications being on. You're welcome, friend. Thank you. Yeah, happy to have more physics, astronomy, astrophysics, cosmology type people and enthusiasts of those topics. That's what we'll mainly cover. So we did a sort of a more plain vanilla type of episode today. Usually we cover, some more, even more. Well, today was not too bad. It was sort of an early history astronomy stuff, but I'm guessing a lot of people might have known about this already. Just kind of went through it, but we also discuss a lot of more, in-depth type of topics as well that are like quantum, dark matter, things like that. So we will do a lot more with that going forward as well. Yeah. Yes, indeed. Just love stuff. Oh, I see. Yeah. I'm not an astronomer, just love stuff like you're talking about. Math was not my strong point. I hate math, to be honest. Oh no! I used to be really bad at math when I was younger. It really wasn't until calculus that I felt like I was good at math. Then I liked it. Yeah, when I was super young, I actually thought I was terrible at math, but I had this like feeling that it was really important and I have to be good at it in order to study physics because I really wanted to study physics. So I probably spent more time like doing and learning and practicing math than anything else when I was younger. And slowly got better, but I especially got better when I was taught math by a physicist, actually. So I was never very good at understanding math as taught by mathematicians, but once a physicist started to explain it, it made more sense. And once I started to take calculus. Good night, Stephen. Good night, Andre. Bye. Good night, Reese. Good night. Death Dragon says I'm still here. Me too, Death Dragon. Me too. I'm going to sleep. Good night, says. Okay. I am going to sleep as well. Okay, Dead Dragon, are you here? It's very late for you, Dragon. If you're going to your papa's house tomorrow, don't you have to be up early? Hi. Yes, about to sleep though. Thank you for joining, everybody. Ava? Who's Ava? I just finished my tea. It became cold by the time I'm drinking it. Oh my god, Dead Dragon. I'm only 3 subscribers away from 3,000. Are you serious? Are you serious? Can you believe this? Hi, Ava. Who's Ava? Hi, what happened? Death Dragon! I'm only 3 subscribers away from 3,000. Do you have any friends? Ava was autocorrect. Oh, okay. Do you have any friends that could subscribe? It was an accident. Either way, thank you so much for joining today. What time are you gonna go to your Thanksgiving party tomorrow? Oh shoot, that's a very big light. I didn't mean to do that. What time is your Thanksgiving party, Dragon? We can chat for a bit. My friend Geo. You don't know? Oh. Okay. Happy Thanksgiving. Have a great time tomorrow. Eat lots of food. I will be doing the same. sure. Maybe. Are you still here, dragon? Me a bunch of food, which is like great. Like the bakery, I just like need the food, man.
কটা বাজে তোমাকে? এখন রাত কয়টা বাজে? কয়টা বাজে বলো? তুমি যে না ঘুমায়, তুমি এই সারা ঘর টাকা বাবু তুমি হ্যাঁ লক্ষ্মী নাম পচা পচা বলে তোমাকে এখন রাত কয়টা বাজে কয়টা বাজে বলো তুমি যে না ঘুমায় লক্ষ্মী
like. Oh,